So my name is Danica Piper, and I'm glad that I have opportunity to welcome you all to the webinar that we organized dedicated to electroceramics. And in the beginning, I would like
I'm going to do a little bit of, start kind of at a tutorial level because I'm sure there's probably a pretty diverse background of people in the audience, and talk about equilibrium defect chemistry, but also partial equilibrium defect chemistry, where the population of defects depends on processing history and mobility of defects and the ability to get to equilibrium. And then we'll talk about defects and potential gradients. And so as we put these materials in a device configuration and there's an applied voltage, let's say, across the material, there's a driving force for defects to move. And we'll talk about the implications of that. And then I'll end with just some newer research in how people are approaching the design of defect chemistry to control properties. Okay. So if you're not familiar with Kroger-Vink notation, that's what I'm going to refer to in this talk, where if we have a reference crystal, let's just say of a metal oxide, 2- anion, 2+ cation, and we have a reference crystal, we'll be using Kroger-Vink notation, where if we have, for instance, a vacancy on the oxygen sublattice, that's denoted by a V. For vacancy, the sublattice is either O for oxygen, or in the case on the right, M for metal. And then the relative charge of the defect is indicated in the superscript. So if we have oxygen, which typically has an oxidation state of 2-, if that site is vacant, then it has a net positive charge. So this is the notation that we'll be using. Okay, so in general, it costs you energy to form defects if relative to the reference crystal. But what we have to remember is, if we look at, and we'll just go through a little bit of refresher thermodynamics, if we have a perfect crystal and we define the Gibbs-free energy of the system, they have your enthalpy and your entropy terms, and this might include things like vibrational entropies of the system. In a defective crystal, you have to consider it relative to the perfect crystal, where the number of defects given here by N, okay, they have a certain enthalpy penalty associated with them. You may also have changes in the vibrational or electronic entropy associated with each defect. And then there's the configurational entropy term. And so we always have to remember, even though it costs energy to form individual defects, the configurational entropy of the system, as that goes up, that can drive down the total Gibbs-free energy, in this case, of the system. And so if in the simple case where maybe you just have metal vacancies in a metal, we're not going to worry about the charge state, then you can find an equilibrium. If you take the derivative of that term, then you have the penalty of forming individual defects that goes up with the number of them, but then you also have the configurational entropy in particular that's driving the Gibbs-free energy down. So there is an equilibrium population of point defects at any given temperature. So it's nice. It's an equilibrium property of the material. Of course, things get a lot more complex when you move to electronic oxides, because you have many defects, they're charged, and it becomes more complicated than in the simple example that I gave. Normally, how people understand, there's a couple of approaches to understanding defect chemistry and materials. And this is an old topic. This is one of my favorite books by Don Smith. But one of the approaches is to make physical measurements like conductivity, which is what's plotted here, the log of the conductivity on the y-axis. And if you measure that versus variables like for oxides, it's usually partial pressure of oxygen and temperature. So I've got temperature changing across this scale. You'll note that the conductivity is a very strong function of both of these variables. And you can infer what the dominant defect chemistry is from these types of measurements. And there's been a number of groups over many decades that have done very careful measurements conductivity, sometimes Seebeck coefficient measurements, sometimes thermographic measurements, to be able to infer some of these thermodynamic quantities about point defects. This is just an example from TiO2 out of the group in Oana, who has a very long history of making very careful experimental measurements of TiO2. And I'll just point to some typical reactions. A very important one is the one at the top, which is equilibrating the material with the oxygen partial pressure in the atmosphere. And so we'll just walk through this one particular one where if I have an oxygen on an oxygen site in the perfect lattice that is net neutral at equilibrium, then I have oxygen vacancies that can occur if I pull that oxygen out into the gas phase. So these are balanced. So basically I've taken an oxygen ion, moved it to the gas phase, left a vacancy, and then I have to have electronic compensations that's charge balance, and that creates 2 electrons. So oxygen vacancies really act as donors in the system. And this is expressed as an equilibrium defect reaction, and you can get an equilibrium constant, or you can write one, the products, the concentrations or activities of the products over the reactants. And we see that we have this equilibrium constant K, the concentration of oxygen vacancies, concentration of free electron carriers, and the oxygen partial pressure. Okay, and if this were the only defect in the system, the only or maybe the dominant defect reaction, then we'd be the total charge neutrality equation would be given by the number of electrons equaling 2 times the number of oxygen vacancies. Okay, and you can do some math and look at how the carrier concentration, in this case, if it's an electronic carrier, should change as a function of oxygen partial pressure from this equation, and it should give you a -1/6 slope. And so that connects back to these conductivity measurements, that if you measure the slopes in different areas, you may be able to infer what the dominant defect reaction is. And again, you can do again, from careful experimental data, you can extract some of these fundamental parameters about the enthalpy and entropy of formation of defects. Okay, so lots of good thermodynamics. If you have those thermodynamic quantities, then you can do things like I've done here on the left, which is plot at a temperature where the system can get to equilibrium, the concentration of all the important or dominant defects in the material as a function of PO2 on the x-axis, and then at some temperature. Now, one important point is when we process ceramics, right, we're usually sintering at high temperature, we're cooling the sample at some cooling rate, you know, depending on how we cool it. Some of the defects may be mobile at low temperatures, some may not. Okay, so we have to think about, if we want to know what the defect chemistry is, maybe at room temperature, where we're going to utilize the material in the device, we have to think about this cooling path and which defects are able to move towards an equilibrium state and which ones are not. And so if you make assumptions that, for instance, in this case, that below a certain temperature, the oxygen vacancies can no longer move, I'll leave that concentration to that at the high temperature equilibrium state, but electronic charge can maybe move around. Okay, and so titanium may be able to go from a 4+, the interstitials from 4+ to 3+, and I can equilibrate electron hole carrier equilibrium, and you can recalculate what these defect concentrations should be at a lower temperature. And that's what I mean about partial equilibrium. And that's really important to know. And a lot of times the kinetics of the process are not understood well. And so, and that's something you have to consider. Okay. The other thing that I show up here, I won't talk about today, is just other physical properties that depend upon defect chemistry. I've shown up here 3 optical images of TiO2 equilibrated at different PO2s, and you can see the optical transparency or absorption properties tend to be very sensitive to the defect chemistry, as you might imagine. And so that can be a signature, another signature of point defect populations. Okay. The other thing I want to point out is if you go really to the bounds of having very large populations of point defects, they can start to order and condense. And in TiO2, you get things like called Wadsley phases, or at certain partial pressures or concentrations of oxygen vacancies, they can form a series of what are called Magnelli phases. But at some point, you can't sustain a certain number of defects, and you can cause higher order defects to form, or even phase transitions. And that's certainly something to consider. And then that also, these extended defects can affect properties, as you might imagine. And this is just an example here on the bottom right, looking at thermal conductivity as a function of the equilibration oxygen partial pressure for TiO2, and showing that right at the point where you start to form these extended defects, you get a lot of photon scattering, and the thermal conductivity drops pretty precipitously. Okay. Now, I've shown you kind of what we call the canonical defect chemistry, where you are able to infer defect chemistry from physical property measurements and calculate some thermodynamic properties. Over the last 10 to 15 years, there's been a lot of progress made on first principles-based defect chemistry, where you can do a simulation of a perfect crystal and then introduce a defect and be able to come up with the formation energy of individual defects. And I won't go through all the math here, but this is a nice review paper from back in 2014. And I've had the pleasure of working with a number of computational material scientists who are doing first principles defect chemistry. And I'll show you a little bit of that, because it can be quite useful if you're wanting to do some design of defect chemistry from a more kind of bottoms up first principles approach. The other thing I'll point out is this is really kind of bringing the semiconductor industry together with the ceramics and community, who we look at. We sometimes don't call them semiconductors, but even good dielectrics ultimately have some conductivity and are semiconducting. But it's important to note that the formation energy of the defects that we're talking about because they're charged, they do depend on the Fermi level of the system, so maybe how it's doped. Also, if I look at oxygen vacancies, the reason that it's changing as a function of Fermi level, because it includes the energy of the charge state, okay, and the ability to move electrons and create free electrons. So in general, these formation energies are a function of the Fermi level of the system, and in this case also the oxygen partial pressure. Okay, but to note that the formation energy depends on this, and that we have regions where we have different charge states are maybe preferred. Okay. All right, so here's an example of, and this is work by Doug Irving, a collaborator of mine who's at North Carolina State University, predicting in a really important dielectric, strontium titanate, the defect chemistry as a function. Again, on the x-axis is partial pressure oxygen, and then at high temperature, where you expect things to be able to get to equilibrium, to thermodynamic equilibrium. And that one of the powers of this is now you can consider many, many defects, not only the majority defects, but you can also understand in different regimes the minority defects, okay, which can be important for some properties. And so this can be quite useful. You can do this same approach where you can allow the system to equilibrate at high temperature and consider which defects are mobile or immobile, and then recalculate back at a lower temperature what the defect concentration should be. But there's lots of information here, okay? Usually these are assumed to be in the dilute solution limit, which is not always practically true, but we have to consider the what the limitations of these approaches would be. But it also allows you to get on the positive side to things like defect complexes, where you have something like an iron substituting on titanium that may want to complex with an oxygen vacancy. And these types of defect interactions can be captured. And I'll just say they're really quite important to consider in the total defect chemistry. Okay? All right. One thing would be, we might ask, these conductivity plots that I started with at the beginning, where we make experimental measurements and infer the defect chemistry, how good are we at, in ceramics, I'll say, at predicting the conductivity? And this is a bit of an eye chart, but it gets the point at in strontium titanate. If you not only consider the more intrinsic defects in the intentional doping, as we did in this case, but also all of the impurities that tend to exist in what I call real ceramics, right? We have background impurities that can be at the 10 to the 17 per centimeter cube, 10 to the 18 per centimeter cube. You have this sea of impurities in most ceramic materials that come to play. And that really complicates the ability for us to make quantitative predictions of defect chemistry or conductivity, because from batch to batch, the mineral source may have been a little bit different, and all of this background impurities can be quite different depending on where you're sourcing your original materials. So I'd say, although we can certainly understand important aspects of defect chemistry from DFT, understand trends, the quantitative values are still challenging in this class of materials because of all these other types of impurities that intrinsically exist. And we haven't had, 50 years of research like we've had in silicon and gallium arsenide and other semiconductor grade materials of really understanding how to purify those materials. And in many applications, it's not necessary. Okay, so that's just a bit of a background on defect chemistry. And how it, ultimately, if you can calculate or measure the charge carrier concentrations and how they evolve as a function of oxygen activity, doping, and temperature, then you have some predictive power to understand the conductivity, both electronic and ionic, of the materials. Now, the next question is, if we take it and we design a material and we put it in a device application, it's probably going to see some sort of gradient. And for electronic oxides, those are voltages that lead to electrical potential gradients. And defects are charged. So if you put them in an electric field, there is some driving force for them to move. And if they can move, that can really affect the macroscopic properties as a function of time and voltage. And it can lead to resistance degradation. For dielectrics, that means that, the conductivity is going up, which in most applications, that is not a good thing, can lead to dielectric breakdown. You can also use it for things like resistive switching, and it affects microstructural and mechanical behavior as well. Okay. So how should charge defects move in an applied field? It certainly depends upon the boundary conditions. For many of the applications I work on, we have closed boundary conditions, meaning that usually ions cannot move across the electrode interfaces for something like a capacitor, or if you're designing a piezoelectric material, but charge may be able to move depending on the electrostatic boundary conditions and whether you have Schottky barriers at the interfaces. If you're working on battery materials, they may be more open boundary conditions. And so the boundary conditions are important to know. I've kind of shown a cartoon of if you have a material at equilibrium on the left here, maybe there is some band bending at the electrodes due to the electronic equilibration. If you put it under an applied bias, then positive defects, like if they're mobile, and oxygen vacancies tend to be fairly mobile, and things like perovskite type materials, maybe metal interstitials, certainly in rutile TiO2, the metal interstitials are quite mobile. They're going to want to move, okay? And then you can build up very large chemical gradients in the sample, again, in this case where you have a closed boundary conditions and not allowing mass transport in and out through the electrodes. And that can be described from a drift diffusion equation. And there's been a lot of research done in this area. You might consider that in regions like this near the cathode, if I pile up a lot of oxygen vacancies, remember what I showed you in TiO2, you might actually push the material outside of its stability, and you might start to form extended defects or other phases near the electrodes, and that can happen. Okay. This, from an electrical perspective, what this looks like, and this has been studied for many, many years, is in things like tantalum oxide, which is a really good dielectric material used in many capacitor applications, things like strontium titanate. What's plotted here and may not be very visible is conductivity as a function of time, and that's what's on the x-axis here. And you might design the material initially to be at a certain conductivity, and usually what happens if the defects are mobile is that the macroscopically measured conductivity will change and often increase as a function of time. And that's shown in tantalum here from work by Klein and Jaeger in the 70s, and also the seminal work by Wasser's group in the early 90s on things like strontium titanate and barium titanate shows this similar phenomena. As a function of time, the macroscopic conductivity changes. Okay. And that's really due to the mobility of ionic defects under a field. This effect has also been used for one type of resistive switching, where the blue, dark blue in these cartoons is meant to indicate a high concentration of charged defects. If they can be moved around, then you can form something like a resistive switch. This is an example where here's your initial state down here, where you just have equally distributed defects. And then once you put it under applied bias, if they start to move, they can move in a filamentary form, which is shown here, or they can be more one-dimensionally. In this case, once these filaments of this more defective and higher conductivity material reach the other electrode, then you have basically a short circuit. And if you take it in the other polarity and you can move the defects in the other direction, then you may disconnect this, and it can form the basis of a bipolar switch in this case. And so this is what, from my perspective, I'd call degradation, because usually in the application space I'm in, I don't want this to happen, but there you can again harness it for different types of applications. There are different, what I'll call three different degradation pathways. One I'll call interface mediated, where if I push the defects up here towards this top electrode, and that dark region just means it's indicating a higher population of defects. If originally this device was defined maybe with a Schottky barrier that was a limiting electron injection into the system, as you modify electrostatically what's happening at this electrode, it may allow for tunneling even at that electrode. And so you may modify what's happening with the electron or hole injection at the interfaces. There's also a region that I'll call bulk mediated, where now if I look just in the bulk, I have regions with high defect populations up here at the top. And often that may be associated with higher electronic conductivity. You have other regions that are have a different concentration of defects that may have lower conductivity. And now you really have an internal junction in the material, and it can actually serve as a PN junction that you've artificially created. Or you can have this more filament mediated degradation that I illustrated in the prior slide. But all of this is the even the pathway by which things degrade depends on many things. First, the initial defect chemistry state, how the material is doped or equilibrated initially. It can depend on microstructure, because you can imagine grain boundaries can be barriers or even fast pathways for defect migration. It depends on the electrode boundary conditions, whether electrons and holes or ions can pass across that boundary. Certainly depends on temperature, applied voltage. One I won't talk about, but it can also depend on humidity, because proton defects, even in things that aren't considered to be good proton conductors, can actually have a measurable effect on defect chemistry. Okay, I'm going to show you an example. This is kind of classic degradation of TiO2, where this is a single crystal that's been biased. I won't show you the pathway, but what you can see is a crystal here, and at the top you may notice that it's really dark. And in TiO2, that's indicative of a reduced region. When TiO2 gets reduced, and I have more oxygen vacancies and titanium interstitials, it tends to get dark optically. Okay, and so I've pushed the defects up here with the voltage, and let's look over in the right. Originally, if I took an IV curve on this sample, it would look something like this, because I have platinum electrodes that form a Schottky barrier, and so it's non-linear because of the contacts. And after I've pushed the defects up here at the top and they've accumulated at one electrode, I don't exactly know what that defect diagram looks like, but I can certainly imagine scenarios where I allow for a strong electron injection, maybe even tunneling at that electrode. And so now, in this state, okay, where it's been really, I'll say, chemically pulled, might be a way to understand this, the contacts are going to behave very differently. And so in one polarity, I now may have linear IV response and it being very conductive. If I reverse the polarity, I've still got a good Schottky barrier down here at the bottom, and so it behaves as it did before. But now I can see in this one polarity, and maybe it was a high resistivity or low conductivity state here, and then it jumps up quite a bit after it's been degraded. And that's an example of really modifying what's happening at the interface in TiO2, which is pretty semiconducting in these conditions. The other thing I'll show that, and I mentioned before, is if you look under those electrodes where it looked very dark optically, here's the electrode, dense platinum. This is that single crystal of titania. If you do electron diffraction, you see superlattice spots associated with all of this contrast here. You can see ordering of defects and actually the formation locally of these Magnelli phases, which are very substoichiometric. Okay. Right. The other thing, I'll just show an example, and this is another crystal. These are just scratches on the crystal. Here's the electrodes. We'll see if this movie plays. May have to get out the laser pointer. Yep. And this will just show a movie where you'll actually see some color changes in the crystal. You see it getting light over here, darker over here, and then you see those filaments nucleate and cross the whole single crystal. This is about 1 centimeter across. Okay, so same material, depending again on the initial boundary conditions and initial defect chemistry state, it can transition to more this one-dimensional movement of defects to where you can actually induce filamentary type degradation. And the last one I'll point out before getting to the final part of the talk is in barium titanate and strontium titanate. Sometimes you can form filaments. This is another case where the optical properties and signatures give you very strong indication of the local defect chemistry. In this case, in iron-doped strontium titanate and iron-doped barium titanate, it turns dark when it's more oxidized. But here you see very large changes in the defect chemistry is inferred from the optical properties, where I have an oxidized side and a reduced side, and I've got this internal junction. And we've done we and other groups have done a number of studies looking at, again, current here. Oops, I lost my laser pointer, turned it off. Current as a function of time during degradation, low resistivity to high resistivity. We can use impedance spectroscopy to get additional information. I won't go into that, but the picture is, you know, qualitatively the same as back when Vosser originally did these works, is that you form an internal p-n junction in the material, okay? And then you'll have very high conductivity in one state, in one polarity, and low conductivity macroscopic in the other polarity. And I'll finalize by talking about just what's going on in the dielectrics community, in particular with respect to things like barium titanate base materials and other electronic oxides that are used in capacitors, where we want to do a couple things. First of all, we don't want it to conduct electrically, we want it to store charge. So we want to limit the electronic conductivity, definitely, but also the ionic conductivity or the ionic charge carriers. And the most important one in perovskites are oxygen vacancies, because even though it may have low electronic conductivity at the beginning of its life after processing, what I've just shown you is in a device application, as those oxygen vacancies can migrate, it can lead to enhanced conductivity. And so we need to control, understand majority and minority charge carriers. And again, we have to live with relatively impure starting materials. I won't have time to talk, but I've already mentioned, we also really need to understand the effect of moisture. There's been some really nice work going on in the community. This is out of the U group and Han group, looking at acceptor donor doping of these materials, where you intentionally put acceptors and donors to help mutually compensate. And if you put in multivalent acceptors like magnesium, which can have different charge states, it can lead to very low conductivity here. And also it can be very, in some cases, it can be pretty independent of the local oxygen activity, and also lead to, this is time-dependent conductivity on the left-hand side, a suppression of the initial conductivity, but also it not changing much as a function of time under a voltage. Okay, these are just other data we've gotten comparing and contrasting things like magnesium, which tends to be single valent to manganese, and you get these very special effects with manganese and co-doped with, in this case, yttrium, or very low conductivity, very independent of PO2. And then we've worked with Doug Irving's group to contrast those with DFT-based first principles calculations, again, looking at magnesium and manganese, where you get this very special effect in the manganese dope, because it has this multivalent charge state. I won't go into all the details, but it's showing you where we're kind of bringing all this together. And the first principles calculations, if you look at now what's shown here, are the free oxygen vacancy concentrations at temperature on the x-axis and then PO2 on the y-axis. You'll see these darker blue colors are very low concentrations of oxygen vacancies that you can get in these co-doped samples. And ultimately that leads to this bottom curves here, which are even under pretty aggressive conditions like 500 C, fairly high electric fields, no apparent dielectric degradation. Okay, so went a little bit long. I apologize for that, but hopefully I've given you a little bit of background if you're not familiar with defect chemistry and its implications for conductivity and dielectric degradation of electronic oxides, and hopefully inspired some of you. Hopefully we have some computational material scientists on the webinar. I personally think this is a great area, and think it's really important for the next generation of defect chemistry design. And I will stop there. Thank you very much.
Thank you, Professor Dickey, for a very, very nice presentation, for a new perspective about the defects and the effect of the defects on conductivity. I really enjoyed, and I totally agree with you about the DFT calculations. I really think that that's very big part of the future researchers. So now I would like to introduce Oana. So please, you can start share your screen.
Okay.
Yeah, and please, I would like to encourage you again, if you have any questions, just write them down in the chat. So when we are done with the presentations, we will go through them and get the answers and discussion.
Okay, can you see my screen?
Yeah.
Okay, great. Okay, thank you very much for this invitation. I'm glad to be here. My name is Oana, and for a few months I'm a postdoc in CentraleSupelec in Université Paris-Saclay. And before I was a PhD student in Josef Stefan Institute in Slovenia. And the few results that I will show you today are from my PhD times. So today I would like to talk about ferroelectric materials at local scales and how we can look at them by means of transmission electron microscopy. So I will just give you a brief introduction on the technique and also on what we can expect from ferroelectrics at local scales. And this is what I mean is nano to atomic scale. And further, I'll give you some examples, experimental results, both on static, but also under external stimuli. And so transmission electron microscopy, it's a high spatial resolution technique. It even allows atomic resolution. And in this case, we have a high energy electron beam, which is transmitted through a ultra thin specimen, and a bunch of signals are generated. And so with the transmission electron microscope, we can have imaging like in any other microscope, and then we can interpret the contrast, but we can also do electron diffraction, and in some cases we can do some chemical analysis. And now ferroelectrics are a large class of electroceramics, and their macroscopic fingerprint is this nonlinear and hysteretic response of the polarization as a function of the electric field. So there is a spontaneous polarization even in the absence of the electric field, and this spontaneous polarization can be flipped. Moreover, ferroelectrics are a class of piezoelectric materials, and in fact, ferroelectrics are pretty good piezoelectrics, so they can efficiently convert mechanical energy into electrical energy and vice versa. And all this functional response is the basis of a large number of applications. This is just a few examples. You might have heard of ferroelectric sensors. Here it's an example of an accelerometer, but they are good candidates for energy harvesting, and the fact that we can have two different polarization states make them good candidates for non-volatile memories. Okay, and so at the atomic scale, at the unit cell level, in a ferroelectric, we have some separation of charges between the center of the positive charge and the center of the negative charge, which leads to a spontaneous dipole moment. And somewhere in between the atomic scale and the macro scale, there is what is called ferroelectric domain structure. So ferroelectrics organize in some regions of spontaneous polarization, and these regions are called domains. And in between two domains, there will be some interface, and this interface is called domain wall. Okay, this is an image, a TEM image of domain structure. And another thing that is interesting to look at atomic scale in ferroelectrics is domain walls, because domain walls are very small features. They can be only a few unit cell wide, and as they are some sort of transition region, they always have distinct properties than the domain matrix. Further, I will show you results obtained with so-called scanning transmission electron microscopy, and I just wanted to make a quick distinction between a scanning transmission electron microscope and a conventional TM, because I think people are more familiar with the conventional TM. So in STM, we have a convergent beam, which is scanned across the sample and the images formed sequentially. And this brings a few advantages in terms of resolution, but also the imaging becomes more versatile. And actually, this is how it really looks like. This is the microscope that I work with, and you can see that it's quite a bulky instrument and that the optical column is a few meters long. In a scanning transmission electron microscope, we can analyze the electrons that are transmitted as a function of the angle, the scattering angle, and this in return gives different information about the specimen. For instance, electrons that are only lightly scattered and are close to the optical axe can be analyzed by so-called annular bright field mode, and this is a good mode if we want to image oxygen. Then further, there is the low-angle annular dark field detector, which catches electrons that are scattered at low angles and gives a strong diffraction contrast. And ferroelectric domains and domain walls are usually strained regions. So this is a good mode to have information about the domain structure. And further, electrons that are scattered at high angle, they come from inelastic scattering on atomic nuclei. So this mode gives a strong atomic number contrast, and it's a very robust mode, so it's usually used for evaluation of atomic displacement and angles and so on. So in order to have some idea about the polar order, we need to make some evaluations from the images, from the atomic resolution images that we have. And there are a few ways to do that. Maybe the most common is by evaluating atomic displacements. And then if we know the Born effective charges, we can actually have a quantitative evaluation of the projected polarization. And just to make this clear, I would like to show you one atomic resolution image and to point out that all transmission electron microscopy images are a two-dimensional projection, and this projection is along the electron beam. So we can see the projected atomic columns. This is a simple example in a perovskite where we can see A side and B side, and the displacement of B side relative to A side is mapped. And here you can see that there is one type of order on one side of the image and another type of order on the other side of the image. And in between, there is some sort of interface, and this is actually the domain wall. And further in my slides, but also in the literature, you often don't see these atomic resolution images, but you see directly the map, the arrow map. And this is just to mention that there are also more straightforward ways. For example, for this stem, which can directly map the electrostatic potential. However, everything I'll show you today is done mostly from atomic displacements. Okay, so ferroelectrics at the atomic scale, we are mostly looking at domain walls because domain walls is where the order breaks. And for a very long time, domain walls have been seen in a very simplistic manner as plain straight interfaces. However, together with the development of high resolution techniques, now we know that they can be quite complex. And for instance, in terms of morphology, they are not always straight plane interfaces, but they can make steps and kinks. And sometimes these steps can be even as large as 10 unit cells. In terms of morphology, in terms of structure, sorry, And by structure, I mean how the polarization is transitioning from one domain to another. This is an example related to so-called non-Ising domain walls. So ferroelectric domain walls were traditionally believed to be Ising-like, which means that there is no rotation in the polarization through the transition region, but only a change in its magnitude. And it's only recently that it was proven in this example, but there are also others, that there is a rotation and this rotation is continuous. And this is another example where you can see that even a more higher degree of complexity was added by showing strain modulation at the domain wall. Okay, so domain walls are sink for point charge defects. So they attract and are attracted by point charge effects. What I'm showing here is a case of conductive domain walls in bismuth ferrite, where this conductivity was assigned by Yale's stem to change of oxidation state in iron, in this case iron 4+, and bismuth vacancies. This is another case where oxygen vacancies segregated the domain wall, and this is a special kind of domain wall because it's so-called strongly charged. You can see that the tail of the polarization meets, which makes it negatively charged, like intrinsically negatively charged, and so oxygen vacancies compensate for that intrinsic charge. But what gives functionality to ferroelectrics is how do they respond to external stimuli. In a simplistic way, when we apply electric field to a ferroelectric, it is considered that domain walls will move as a consequence of polarization switching. And in most cases this happens. However, we know now that some domain walls are not mobile. But what's more is that even at so-called weak fields, so before the long-range movement of the domain wall is activated, we can still have some change in the local properties of the wall. This is one example where the domain wall plane is changing, which leads to change in the domain wall conductivity. To see this locally, we have to combine the STM technique to the possibility of applying some different other environments, for example, temperature to check phase transition, or electric field to check the domain dynamics. I know it's also possible to change the atmosphere, for example, introducing oxygen-rich environments, but I have never worked with these holders, so I will focus on heating and voltage bias. I will start with relaxer ferroelectrics. I don't know much about relaxer ferroelectrics as I just started working with them, but I'm just learning. But I think it's a very good example where it's important to know the local polar environment in order to understand the functional properties. So such materials are slightly different than ferroelectrics. For instance, they have a more diffuse phase transition, and I'll further refer to the prototype of relaxer ferroelectrics, which is lead manganese niobate, lead titanate. And for concentration range of lead titanate, we can reach morphotropic phase boundary where phase coexistence happens, and this is associated with a large piezoelectric response, considerably larger than classical ferroelectrics. And from the very beginning of relaxer ferroelectrics, one model has been proposed, and that model is a polar nanoregion model. And this model has been actively used in simulation for decades, but it starts to be questioned whether or not we need this model, especially because it does not come from a direct observation. So polar nanoregions the polar nano-region model was useful in explaining the response. However, it was a very speculative scenario. Okay, and more recently, another model has been proposed, and that is polar nanodomains, where instead of having a non-polar matrix, everything is polar, but the domain walls are low angle, so-called low angle domain walls. And it has been only a few years that this model has been confirmed by STM, where these low angle domain walls have been spatially correlated with chemical heterogeneity, but also with oxygen octahedral tilt, oxygen distortion, and lead sublattice distortion. So the large piezoelectric response and the correlation with local compositional disorder and the correlation with the polar order has been breached. And this is just a part of my preliminary results that I currently work with. So I often find in this morphotropic phase boundary composition some sort of hierarchical structure where I have these rectangular like large domains which separate regions where the polarization in average points in 110. It has a 110 like distortion on one side and a 100 like distortion on the other side. And locally, I find often polar clusters. And then my intention was to apply them to heat it up in situ and try to understand what is going on. For the moment, I did not manage to get atomic resolution, but what I saw is that when I have these large rectangular domains and the more fine structure, first the fine structure disappears, suggesting one type of phase transition, and further at higher temperature, there is no more domain structure, so reaching paraelectric state. Okay, this is one example when we are applying electric field in situ and looking at what happens with the domains and with the domain walls. This is the case of sodium potassium niobate single crystal, and this is a sequence of TM images at different voltages. Just to be easier to follow, I colored the different domains. And here I have three types of domains, the red colored one, the blue ones, and the matrix. And when electric field is applied, on this polarity is the red domains that grow. And we can describe how the growth and nucleation takes place. So in this case, it's always from the tip of the needle-like domains. The growth is forward until the domain meets an obstacle, and then they start to grow sideways. And in this case, there was no back switching when we came back to zero. However, on the minus polarity, so switching the electric field, the behavior was slightly different. Now the blue domains were growing, and it had a traditional forward growth until a certain voltage, when the number of domain walls suddenly increased, and a lot of splitting took place, and we believe this happened because of stress accumulation. So, for instance, if I would plot the area of the red domains, which I know they are corresponding to one orientation of the polarization as a function of voltage, I get something that resembles a macroscopic hysteresis loop, and this is because the area is proportional to the polarization. And so it is a local indirect evaluation of the ferroelectricity. And there are some noise in this hysteresis loop which correspond to some soft pinning events. Like in this case, when two orthogonal needle-like domains meet. And I would like to end with one study that is done at the atomic scale, which follows the movement of one single domain well. In this case, is a bismuth ferrite single crystal. And I know that for bismuth ferrite, the coercive field is quite large. In fact, we were wondering if we could even reach it under in this experimental setup. And so when I applied electric field, I didn't know quite what to expect, but I noticed that this contrast which marked the position of the domain well didn't quite disappear with the electric field, but it more smeared. So I thought that what we are doing is we change the structure of the well without having a long-range movement. However, when looking at the polar maps, I saw that we have switching of polarization, and this switching is in accordance with the direction of the electric field, and this was true for more than one cycle. So now it made us wonder, what is this strain contrast associated with? And this is just a possible hypothesis, is that we are moving the physical position of the well, but point charge defects responsible for strain stay behind. And then we try to see what kind of possible defects we have. By years, we rule out iron 4+, we rule out segregation of bismuth vacancies, but we did find a little bit lower intensity of the oxygen edge. So we believe that the possible hypothesis is that we have segregation of oxygen vacancies. Okay, and this is again in bismuth ferrite single crystal, one triangular-like domain well. And with the electric field, we are able to change the plane of the well and induce some changes. For instance, we have strain redistribution, but we believe we have also bismuth vacancies redistribution. And because we are changing the plane of the well, but we also change the magnitude of the projected displacement, we can create different bound charge distribution. Okay, and with this, I would like to conclude. I think that STM is a good technique to bridge the macro scale and to the atomic and nanoscale mechanisms. However, because I did not talk a lot about sample preparation and about the experimental setup, I'd like just to mention a few limitations. So first of all, it's a local technique, and this is good because this is what was our intention in the first place. However, the reverse is true, that local techniques, local measurements should be approached with caution, and maybe this could bring poor statistics. So it's always better to put it in the context of the measurement. Then the samples are quite thin, and then the experiments are in vacuum. And for the in situ part, at least for the state-of-the-art holders that we have now, I think that the control over the electric field is still quite poor, and that maybe we need some finite element simulations and so on in order to understand the electric field distribution, but also to link it to the response. And with this, I would like to thank you very much for your attention.
Okay, thank you, Oana, for great presentation. I believe that all of us will enjoy really. So now we will go to the part with the questions. So I'm not sure, I opened the chat, but I didn't see any written questions. So I would like to encourage you to, if you want, you can raise the hand or write again. Oh, okay, we have one question. So from Sonia, thank you, Sonia, for the question. Thanks to both speakers for great talks. I would like to ask if Professor Dickey could share more about her experience related to the effect of humidity. So,
yeah, sure. I'd be glad to. And this isn't published yet. We're still writing up the manuscripts, but and there's other work out there, even on, as I mentioned, we're looking at materials that are dielectrics. They don't have good proton conductivity. So there are some perovskites that are designed specifically for being good proton conductors. Even in things like barium titanate, what we have studied is that if you measure, again, using conductivity measurements and impedance spectroscopy, as you put a step function on, let's say, the PO2, so we go from dry conditions to, I don't know, 40 millibars, something like that. I'm forgetting the exact numbers. I can pull up some data, that you see a relaxation of the electronic conductivity we find highly reversible. And it's from protons basically being able to come into the system. So the water can dissociate maybe at the electrode, and protons can come in, and they act as donors. And if it's already N-type, it will increase the electronic conductivity. If it started out P-type, it will decrease it. Highly reversible. A really interesting thing is that if you're at a lower temperature, let's say in barium titanate at, let's say 100 or 200 degrees C, you'll just see this one-fold relaxation, that the protons are coming in, getting to their equilibrium concentration, changing the electronic conductivity because they're donors. If you're up above 450 C, that's kind of the target temperature, 450 to 500 C, where oxygen vacancies become mobile. And if you're above that temperature, you'll see a twofold relaxation. You'll see the protons come in, change the electronic conductivity. But because you're changing the Fermi level of the system, it changes the formation energy, the oxygen vacancies, and then they respond. And so you'll see it maybe go down and then back up as the oxygen vacancies can come in and out of the system. So it's really interesting phenomena. But even, I just say, materials that you don't think you have to worry that much about the proton conductivity, if you get enough protons in, it changes the electronic conductivity because they act as donors.
Okay, thank you. We have one more question. So again, thanks to both speakers for interesting talks. My question is to Oana. Does electron beam influences the domain wall in any way? I'm wondering if high intensity of electron beam can interfere your observations. Thanks. And then after that, we have one more, but maybe to answer the first one. You can open the chat and read it again.
Okay. Well, from my experience, I never saw any movement or any change in the domain structure with the electron beam. However, it's true that maybe there is a slight heating, but from my experience, I have never seen any change in the domain structure with the electron beam.
Thank you. I have one question. Maybe it's a bit it's not out of topic, but for Professor Dickey, do you know which software do you use for DFT calculations?
So I am not a DFT expert. I collaborate with very competent people. So I think most of the people I've worked with use VOSP, but
VOSP.
Yeah.
Okay. Yeah. Perfect. Thank you. Also, I have one more question. Maybe I missed somewhere, but we just start working with that, so it will be nice to hear from you. How do you experimentally investigate the defects? For example, in thin films, for the thin films thickness about 10 nanometers, what would be the technique for experimental investigation?
So if you can, conductivity is one of the most sensitive measurements for sure. There are people who are also using optical based measurements. So obviously that's going to depend on your substrate, but if you could judiciously choose a substrate that, you know, maybe is not absorbing over the right wavelength ranges that are appropriate, then you might be able to do some optical absorption. And I know that the group out of Illinois is doing a lot of that. So optical and electronic conductivity measurements tend to be the most sensitive. You have to have pretty high concentrations by the time you can measure them by things like TEM. And I showed some examples where you have very high concentrations, but you know, when you're at the 10 to the 17, 10 to the 18 level, it can be really difficult to measure them by imaging techniques and spectroscopy, and I'd say electrical conductivity measurements tend to be the most sensitive. We have done some cathodoluminescence spectroscopy, so that can give you, I mean, photoluminescence, cathodoluminescence can be quite useful too.
Okay, thank you. Do we have some more questions? I don't see in the chat. Okay, we've had questions about the yes, the recording will be posted online, so if anyone wants to know or to rewatch and to listen again. Okay, then if we don't have any further question, I would like to thank again to both of the speakers. Thank you for amazing presentations. I believe that we really enjoyed. And thank you once again for accepting the invitation for giving a talk for our webinar. It was a great pleasure to listen to both of you. So that will be it for now. Thanks again. If you have anything to add, please feel free.
Very much.
Thank you.
Thank you. Have a nice afternoon.
You too.
Thank you.
See you. Thanks.